Yeah. Okay. So I will share again. I want to start saying that someone asked me before about other Frobenius algebras, and I say that yes, that this is something that is what is related to what Kovanov-Rosansky homology is about. And it was not Kovanov-Rosansky, I was confused. It is Lee's homology. Okay, Lee, L-E-E, Lee's homology is taking another Frobenius algebra instead of the one sending v minus to 0. Okay, so now we go back, and I will start with the second part of the talk, which is about Alexander polynomial and not Floer homology. So well, this is not, yeah, no. Okay, so as before, I will start with some properties, some applications of Alexander polynomial. As I said before, this was the first polynomial invariant that was discovered. It was discovered by Alexander in 1927. It's well, it's a polynomial with integer coefficients and t plus minus 1/2. The Alexander polynomial of a link of its mirror image, meaning recall the link when you reflect it in a mirror, and the link with the opposite orientation is the same. Okay, so Alexander polynomial doesn't distinguish between those three links. It's an invariant of oriented links, as I told you, as the same as happens with Jones polynomial. If it behaves well with connected sum is just, imagine you have two trefoils. The connecting sum is just you remove one a little arc and you just connect like here. Okay, this is the connected sum of two knots. You understand the idea, right? You have two knots, you remove a little part of the strands and just connect them, not creating any crossing. This is connected sum of the Alexander polynomial of the connected sum of L1, L2 equals the product of both Alexander polynomials. Alexander polynomial satisfies a scale relation, and the scale relation, well, it's this one, okay? And this, how to interpret this thing that I wrote here. Okay, imagine we have a linked diagram. We have three link diagrams differing just in a neighborhood of a crossing, where in one of the diagrams we have this picture, in other of the diagrams we have this picture, and in the third diagram we have this picture. Check that L0 is the only smoothing preserving orientation, right? If you are here, the only way that you preserve orientation is taken to the left, and if you go here, is taken to the right, right? The same. So if you have three link diagrams differing just in the neighborhood of a crossing in these ways, then the Alexander polynomial of the first one minus the Alexander polynomial of the second one equals this power times this factor times the Alexander polynomial of the third one. I will repeat again. This is L plus is just positive crossing, L minus is just the negative crossing, and L0, I'm going to repeat it again. Notice that this doesn't depend on which part of the strand goes up and which one goes down. This smoothing depends just on orientation. Recall that before we saw the smoothing for Kaufman states that doesn't depend on orientation, just depend on which parts goes up and which parts goes down. This is the opposite. Here, we don't mind with who goes up and who goes down. We just mind orientation, okay? This is the only smoothing preserving orientation. So yeah, Alexander polynomial satisfies this scale relation. If we define this invariant, the genus of a link is the minimal genus taken among all orientable surfaces whose boundary is the link, okay? Well, there is a theorem that we will say later, a Seyfert's theorem, telling us that every link can be seen as the boundary of an orientable surface. So take all orientable surfaces spanning the link, take the minimal genus, and this is going to be the genus of the link, okay? So the breadth of Alexander polynomial is lower or equal to 2 times the genus of the link, okay? The breadth, I mean the maximal minus the minimal power of the polynomial. If a knot is fiber, then Alexander polynomial is monic. So yeah, these are the some properties. And now let's go to the definition of Alexander polynomial. Again, we will do an example, our favorite example, which is the trefoil. Okay, so we have a diagram, and we want to associate to the diagram a polynomial. I'm going to show you the geometric definition. The original definition of Alexander was what is nowadays called the combinatorial definition. There is also an algebraic definition related to the knot group, meaning the fundamental group of the complement of the knot. But since we have not much time, we will just see one, and I chose the geometric one.
Marithania, can I ask something?
Yes.
Can one see the fundamental group of the complement in terms of scalar relations of some type? Like, can you relate not complements different?
I don't know. I haven't seen anything like that. So, but I don't know.
Okay. Okay, thanks. It was just a random question. So.
Okay.
Thank you.
So the geometric definition to a diagram, we want to associate a polynomial. So in the way we are going to associate to each diagram a surface, then to the surface we are going to associate a matrix, and then to the matrix we are going to associate the polynomial. So this is the path we are going to follow. Okay. In the first part, we will use Seyfert's theorem, the one I told you that to each link you can associate a surface spanning the link. Then from surface to matrix, we will use something that is called the Seifert pairing. We will see what is that. And then from matrix to polynomial, we just use determinants, which is good because this is known, is very well known. So let's start. So Seyfert's theorem tells us that every link bounds an orientable surface. And we will see the proof because the proof is constructive. So, and we will need it for computing the Alexander polynomial of the trefoil knot. So we start with a link. Our link is going to be the trefoil. And we consider a diagram of the trefoil, and we give an orientation to the diagram. Okay, so I chose this diagram of the trefoil knot, and I chose this orientation. And now, each time we have a crossing, we are going to smooth the crossing by following the only smoothing preserving orientation. Okay, as I stressed before. So there is no problem. There is no who goes, which part of the strand goes up, which part of the strand goes down. This is not important for us. We just need orientation. So in our case, I draw more arrows so you can see easily orientation. If we go here, then if we want to follow orientation, we have to come here. And if we are coming in this direction, we have to come here. So we have this. We are going to do this in the 3 crossings. So now in this one, we have this. You see, we are just following orientation. And then in the 3rd one, we have this. So again, we end up with a set of circles. And this is not something that I can choose as before. No, once I choose the orientation, this is the smoothing I have, the Seifert smoothing associated to the diagram. And now to each circle, I'm going to define this map associating to each circle the number of circles containing it. So in my case, the outmost circle is not containing any circle, so I have 0. And this circle, the inner one, is contained in the other one. So to this circle, I associate 1. Okay. And now we are going to construct the surface, and we construct the surface in the following way. For each circle here, we are going to draw a disk, and those disks are going to be in different heights, at different heights. So the height is going to be this green number given by this h function. Okay. So in this case, this 0 circle, the outermost circle, gives us this disk at level 0, at height 0, and then at height 1 we have the other disk. Those disks inherit the orientation of the circles. And now we are going to add a band, either twisted to the right or to the left, in the place where there was a crossing. So here recall that there was a crossing, so we had to add a band. Here there was another crossing, so we had to add another band. And here we had a crossing, so we had to add another band, right? Notice that I twist the band to the right or left depending on the crossing I have here. Okay, I'm preserving the orientation of the crossing. So it is trivial to see that the boundary of this surface is exactly the boundary of the link. Is exactly the link. The link is spanned by the surface, right? Because you have the circles and then you have the bands where you have a crossing. So this is the proof of Silvero theorem. To every link, you associate the diagram, and then with the surface, you see immediately that the boundary of this surface is exactly the diagram you had here. So is the link. The boundary of the surface is the link you're starting with. Someone could ask, well, but what about orientation? How do I know that this surface is oriented? Well, you just need to check that when you have this as div at equal height, then the bands have different orientations. The band connecting them has different orientation. And when you have the bands between these of different heights, the bands has the same orientation, meaning that, for example, if this is red, then you have here red, then here you have, not the bands, when you have these at the same height connected by bands, then this has different orientation, meaning that when you twist the bands, everything agrees, right? And when you have bands connecting these at different heights, then these, as here, had the same orientation, meaning that when you twist the band, everything works, because if this is red, then this is, let's say, blue, but this blue is connected with below the part that we don't see. So the surface at the end is oriented, right? So this is the proof of Silvero theorem. So we started with a link diagram and we had a surface. So by using Silvero's algorithm. So this is the first step. And now we need to go from the surface to the matrix. And to do this, well, the first thing we have our surface and we want to thicken the surface a little bit, okay? In such a way that, well, we use this homomorphism and S times 0 is the surface. Let's say that the core of this thickening is the surface itself. And we decide that the positive side is going to be the S times 1, the image of S times 1, okay? So we have our surface, which is thickened. And now,
Marithania, one quick question. So someone on chat is asking, they think like maybe there was something funny about the picture. They were confused about the orientation of the twists, I think.
Yeah, it may be. Let me check. What
the left one twist?
This one?
Broken? Yes.
No, I think not, because we are. Imagine that this is pink and down is gray. Okay. So if you, do you see me? Am I invisible? Yeah. Yes. So you are coming down, gray, and now the bands does this, no?
Yes, so the color is correct?
I would say yes, because the
right is different, I think, or?
So this is pink, and down you have gray, right?
Yes.
So the band, when the band does this, sorry, you are looking at me that way. Okay, so the band does this. So this size that you see of the band is connected to the down, the part that you are not seeing of the disc. Do you understand what I mean?
Yes, I agree.
If you have water here and water falls, water comes here. Goes in the other side that you are not seeing of the band. So this is pink comes in the other. I don't know if this was the question.
But I mean the twist. It's a right twist.
Oh, the twist. Sorry, I thought the color.
Orientation.
No, the twist is correct. I will tell you why. If imagine this upper circle. Well, one reasoning that will be very easy, and you say, okay, will be just that this node is alternating, this diagram is alternating, so this has to be alternating. And if this one is upper, this one is up, then the next one you find is this one, and this has to be down.
But it's from the other side?
But if you
look at it from the back,
it may let me think 1 second. What?
Yeah. It's not the main
maybe
point, of course, but
yeah, it may happen that you yes, you're right. Yes, sorry, I thought you meant at first. I thought you meant the orientation, and then, yes, you are right. You are right. If you do this, if you do the first circle smaller and you look from the top, then you are right. This should be the upper one, meaning this. But of course, this, if you have made the upper one smaller, then you look this from the other side. So yes, you're right. This should be the opposite crossing. Yeah.
Thanks.
Yeah. So sorry for not understanding you at the very beginning, and then for doing wrong the picture. Yeah. Oh, but this means that you are super paying attention, which is good. Okay. Yeah, this crossing should be modified. So we have the surface, and I think we were at this point, right? So we had a basis of the first homology group of the surface. These are K-closed curves in the surface, which are these bases. And now we are going to define this Seifert pairing, which is a map between, it sends two generators, two curves in the basis of the first homology group of the surface, so two generators, and they are sent to the linking number. Recall from the first part of the talk, this linking number of the first one and the lifting of the second one. Okay, this positive means the lifting. Recall that this is a thickened surface, so just lift it to the positive side of the surface. Okay, so you have two curves that may be linked, so just consider the linking number of these two curves. And this is going to be the entry in the positions ij of the matrix. Okay, so let's see our example. Well, here it is correct because I decided to see the surface from the top. Okay, so this is this surface with this little mistake. Okay, so this surface, if you see it from the top, you get this. Okay, so I just draw the surface this way because I thought it would be easier to explain this. So now we consider a basis of the first homology group of the surface. We have those two curves, A and B. We could have chosen other bases, but I have chosen this one. And now we want to get this Seifert matrix. So what we do, we say, okay, let's consider, here I have just two curves, so I have 2 times 2, 4 entries in my matrix. So I draw these two curves are these ones. Here, since the bounce is twisted that way, A always goes over B, okay? And here, since both curves are in the surface, then they intersect in the surface. So this is the picture I have of my curves. If I forget about the surface, this is what I have, okay? So now, if we lift B, then B goes over here. So I will have two positive crossings. So this could, if I compute the linking number of those A, B plus, I will have 1 plus 1, 2. Since I have to divide by 2, I get a 1 here. Okay? Now, this was my original situation. If I lift now A, now this is negative. So I get the linking number of B, A plus is 0 because I have one positive, one negative. So I have a 0 here. And well, if you do A and A plus, you just lift A, you get two negative crossings. So you get -1 And if you do the same with B and B plus, then you get -1, okay? So this is the safer matrix. And we are here. So we started with the diagram. We had our safer surface. From the surface, we constructed the matrix. And now to get the polynomial, we just get the determinant of this matrix minus t times the transpose of this matrix. So this is just computation. If you do this, you get that 1 minus t plus t squared. Okay? And Alexander proved that this is a link invariant. This is Alexander polynomial. And since it is a link invariant, instead of d, we can just write L. And is a link invariant up to powers of, up to product by plus minus t to the k power, up to product by powers of t, okay? So what we usually do is that we symmetrize the polynomial. We say, okay, we have 1 minus t plus t squared, we symmetrize it. This can always be done for the knots. We can always symmetrize Alexander polynomial, and that is what we get. Okay, so we say that Alexander polynomial of the trefoil link is t minus 1 plus t. Okay, and this is the way how we compute Alexander polynomial of the trefoil knot. The proof is very nice because, well, it is we use a result saying that that two surfaces represent the same. I mean, if you have two surfaces with boundary, their boundaries represent equivalent links if and only if the surfaces are related by a finite sequence of course, isotopies, and adding a tubing, and compressing, meaning cutting a cube and putting 2 copies of, surgery, okay? Tubing and compressing. So this is what is used to show that this is a link invariant. Yeah, this is the geometric definition of Alexander polynomial. And now I will show you another definition, the grid definition. And in order to give, I'm going to give this definition because then I want to explain grid homology. So let's see the definition of Alexander polynomial in terms of grid diagrams. So first I will explain what is a grid diagram. A grid diagram is just, we have a grid like here. Here we have a 5 times 5 grid. And now we are going to put some crossings. We need to put a crossing in each row and a cross in each row and a cross in each column, and some circles, 1 in each row, 1 in each column, like let's say a Sudoku, okay? And now we are going to connect them in that way. First, in vertical, we recall that we have 1 cross and 1 circle in each row. So we go from the cross to the circle in this direction, from cross to circle. So in this case, we have something like that. And now in this in columns, and now in the rows, we are going to go from circles to crossings, to cross. So in this case, from circle to cross, we have this. Here, we have some intersection here. So the green one, the horizontal one, always goes down, okay? And in this case, well, we have something like this, okay? So in this case, what you really have, this is a diagram of trefoil knot. So once more, we have the trefoil knot, okay? This can always be done. Why? Because, well, if you have the crossings that way with the vertical one going over the horizontal one, then this is correct. But if you have something like here where the horizontal one is the one going over the vertical one, then you can do this trick, okay? And then the green one becomes vertical in the crossing and it goes over. So at the expense of increasing the size of the grid, you can always get one of those construction from any link, okay?
Marithania, can I ask a question?
Yes.
Sorry. So because like when you look at Legendrian knots, one does something very similar. Like one always has crossings in a preferred kind of direction or kind of thing. And one does exactly the same thing. Like if you need to, then you introduce kind of like an extra turn to make them turn in the correct way.
Okay.
So is there like a relation? I mean, do Legendrian knots appear in secret somewhere here?
I don't know, but I don't know. I would say that this is more this is simpler. I don't know. I haven't seen.
No, it just seems very similar, this phenomenon about preferred kind of crossings. So I don't know. Okay.
Sorry.
No worries. Bless you. Thanks.
Thank you. So yeah, maybe there is some relation, but I haven't seen Legendrian knots in those contexts. So I mean, in the context of grid diagrams of this grid definition. So from here, you can define new link invariants. For example, the minimal size of the grid. That, I mean, the minimal size of a grid, so that you can get a grid diagram of a node with this size of the grid, right? Do I explain I mean, maybe this is easier to understand that when I try to read it. So for the trefoil node, this grid number is 5, meaning that you cannot do trefoil node with less than 5 times 5 grid, okay? And for the Hoff link, you have a grid number 4. But of course, when the number of crossings is higher, this explodes and the size of the grids are very, very big, okay? So we have this theorem by Cromwell of 1995 saying that if we have two grid diagrams representing a link, then, I mean, two grid diagrams represent the same link if and only if there exists a finite sequence of grid moves connecting G1 and G2, okay? And those, well, we don't go through that, but just to show you that we have this sequence similar to that of Rademacher moves or Markov moves. So here it happens the same. If two grid diagrams represent the same link, then you can go from one to the other by a sequence of commutations, stabilizations, and destabilizations. Well, you can imagine more or less what commutations is. It's something like pushing up or down two rows that are two columns that are far away. And stabilizations and destabilizations is a kind of move changing the size of the grid. Okay, so yeah, this is a result telling you when two grids represent the same link diagram. And well, let's see Alexander polynomial from this grid definition. So we need to define the winding number. The winding number, if we have a closed curve in the plane, okay, and we choose a point, then the winding number of this point, according to this curve, is you just count 1 each time the curve goes around the point clockwise, and -1 the times for each time that the curve goes around the point counterclockwise. So in this case, A, if you start and you do the curve, you see that you just go once around A1 counterclockwise. So you have that the winding number of A is -1, okay? If I choose, for example, B here, if you do the same, you will see that you go twice around B, okay? The curves goes twice around B at counterclockwise, okay? So the winding number of B is -2, and with C, well, you just have 1 in this direction, in this sense, so you have -2. And an easier way to see this, instead of going around the curve, is just to, for example, to know the winding number of B, just draw a segment starting in B and going through the non-bounded component. So go out, and then just count the number of intersections and see if those intersections goes clockwise or counterclockwise. Okay, so in this case we have 1 and 2 counterclockwise, so we have -2 for B. Okay, so this is just to define you the winding number of a point which is defined according to a closed curve. Okay, So we have our grid, we have our diagram in the grid, and now in each of those intersection points, in each of these, we can say that we have like a lattice. We have here those intersection points, this grid. Then we are going to write the winding number in each of those points. And the curve is, of course, the diagram of the knot that we have, okay? So for all these points, for example, for the ones that are out of the curve, of course, we have 0, 0, 0, 0, 0, because no one is going around them. For the ones in this region, the curve is going once counterclockwise. So we have -1, -1, you see? Here we have +1. And here, for example, we have 0, because we are going once, we are not going around it. This curve is not going around it because it doesn't close, the 0 is out. And then with this part of the curve, the same happens. So here winding number is 0. Yeah. So, well, we have this for each point of each intersection point in the grid. And now we are going to construct a matrix, which is going to be T to the winding number power. So in this case, we have this matrix. There is a mistake before you find it. Here we have T, we have 1, 1, 1. So this, and this should be T, 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 okay? I found that, but I didn't have time to check it. So this should be T, T, T. And here we have T minus 1, T minus 1, T minus 1. I mean, it's just T to the whatever it said here, power. Okay? Okay, so now, well, sorry, I forgot to say that you remove the upper row and the rightmost column. Okay, you remove this and this, I cross them with red, and then we have this matrix, and then we need this index. A is going to be the number, the sum taken of all the numbers which are in the corners of X and of circles. So in this case, quotient by 8. So in this case, just take X and circles, keep the numbers that are in those squares, in the corner of the squares where you have either a cross or a circle, and then add all of them, and then quotient by 8. And this is going to be A. Okay? In this case, we have the same number of ones as of -1. So when you add them all, you get 0. So in this case, A is 0. Okay? And now the Alexander polynomial is defined that way. Take the determinant of this matrix, multiply by this factor. This n is the size of the grid, in this case 5, and multiply it by t to the a power, where a is this number we have just said. So if you do this in this case, we have the determinant of this matrix times this. I wrote -4, sorry, this should be -5 times t to the 0 power. And if you do this, you get this polynomial, and this is the Alexander polynomial in the symmetrized version, right? This is a link invariant, and Osvat and Savo proved that this Alexander polynomial in the symmetrized, you don't need to symmetrize it, okay? So we get the same as before, of course, because it's Alexander polynomial that we compute before. It sounds like magic, but it's not magic, okay? So yeah. Should I continue or some question with this? Yeah, okay. So now let's go to not Floer homology. Okay, so not Floer homology was introduced by Osvat and Savo in 2004. It is a big-graded homology. Again, we have two gradings. It is a link invariant. It categorifies Alexander polynomial in the same way as before, as with John's polynomial. The Euler characteristic of not Floer homology is Alexander polynomial with some factor, okay? We need to multiply by some factor, but it's the same idea. is not preserved by taking mirror image or mutation. So Alexander polynomial is preserved by mirror image, but not Floer homology, not. It admits an exact scaling sequence, meaning that if three links differ in, well, if three link diagrams differ in a neighborhood of a crossing in that way, then their not Floer homologies can be put into a exact scaling sequence. They satisfy some relation. Well, the genus, recall that Alexander polynomial gives us a bound for the genus of a knot. So Alexander polynomial gives us a bound, but not Floer homology detects the genus, okay? Not Floer homology, the maximal second grading, quantum grading, so that the homology group is not trivial, gives you the genus of the knot. Not Floer, since the trivial knot is the only one having genus equals 0, and not Floer homology gives you the genus, then not Floer homology detects the trivial knot. It also detects both trefoil, the right-handed trefoil and the left-handed trefoil, and the figure 8 knot. The same as I said before. This means that if you have a knot and its not Floer homology equals the not Floer homology of the right-handed trefoil, then this knot is the right-handed trefoil. Okay. Well, if detects when the knot is fiber, this is an if and only if condition. And from not Floer homology, you can compute this tau invariant, giving you a proof of Milnor conjecture, and telling you that, well, if two knots are concordant, then their tau, they give you a how do you say, sufficient, an if and only if condition to know where two knots are concordant, okay? So two knots are concordant if and only if their tau invariant is the same, okay? So these are just properties and applications of not Floer homology. And now let's see how we construct it. So I'm going to show you first the original definition, but it uses, at some point we need some symplectic topology, so I'm not going to go through that because I'm not an expert on that, and also is quite complicated. So at some point we will change to another more combinatorial definition. So let's start with the original definition. We need to know what is a Heegaard diagram of a knot, and a Heegaard diagram of a knot consists of 5 elements. Okay, here we have the 5 elements, and we will see what is each of them. So the first one is a surface of genus G, and this surface splits the S3 into 2 handle bodies, U0 and U1. Okay, so I'm going to explain here what is each element here, and here I will do an example. So for example, imagine that my surface is the torus. I have the torus, and this surface split S3 into 2 handle bodies, into the inner solid torus, and outside I have other torus, right? Other solid torus. So this is my surface. Now alpha is going to be a family of G plus K minus 1 closed curves. G is the genus of this surface, so it's fixed, and K is a number that I choose. Okay, I can choose any K that I want. So, well, more or less, but I can choose any K. So I have this family of closed curves. They should be disjoint, and each of these curves bounds a properly embedded disk in U0, in one of the 2 handle bodies we had here, okay? And the complement of those disks is a union of balls, okay? So in this case, imagine U0 is the inner torus, the solid torus that we have inside this sigma. So if I choose K equals 1, this is something that I choose. I just need 1 curve because the genus is 1 plus 1 minus 1. I just need 1 curve. So this is going to be alpha 1. And well, I have just a ball. I have just, this is the boundary alpha 1 is the boundary of the meridian this of the torus, okay? And this is properly embedded in U0. And I have one ball here. This is B1, okay? Then beta is going to be exactly the same, but instead of those Ds to be properly embedded in U0, they are going to be properly embedded in U1, okay? So imagine this is beta 1. This could be just, you can think of it as, yeah, I mean, this is beta 1, and you have the same. You have one ball in U1, and sorry, the complement of this bounded by V1 is one ball in U1 in the outer torus. Okay, so well, we have this surface, those two families of curves. Now W is going to be a collection of points which are going to be disjoint from each other, okay, and disjoint from both curves. So, for example, I choose W1 here. I have K, so since I chose K equals 1, I have just 1 point, W1. And Z is going to be the same, a collection of points disjoint from each other, disjoint from the curves, and disjoint from the W points. Okay, so in this case, I have here Z1. Okay, so this is a Heegaard diagram of a knot, but what is the knot? Which knot do I have here? So to see which knot, I mean, I'm telling you that this is a Heegaard diagram of a knot, but what should happen with the knot once you associate to it a Heegaard diagram? Okay, so the knot intersects the surface just in the Z and W points. So in this case, just here in Z1 and in W1, the knot intersection U0, meaning intersection the inner torus, is going to be K intervals, 1 in each of the balls, and the knot intersection, the other handle body, U1, meaning the outer, let's say, torus, is going to be K intervals, 1 in each of the balls. Here, recall that I have 1 ball in U0 and 1 ball in U1, so I will have 1 interval in U0 and 1 interval in U1. So the knot here, we start imagining in Z1. Now, Z1, we go, let's say, out of the surface. When I say out, I mean what everybody is understanding, not the solid torus that is inside sigma, but the other one, right? The one which is outside. So we are in Z1, we are, let's say, out, and since we are out, we are in U1, we cannot intersect beta 1, and we need to reach W, because this is the only way that we can again intersect the surface and go into U0. Okay, so we go out, 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 out. I cannot cut beta 1, so I need to go around. And now I'm out, out, I'm in U1, U1, U1. And finally, I can go to W1, so I intersect the surface, and now I'm down. And now I'm inside, I'm in U0. And now I do the same, but now the curve that I cannot cut is alpha 1, right? So now I am here. Since I'm inside, I go down because I'm inside. I continue. Since I'm inside, this part is closer to my eyes. So this is like that. I mean, till you reach Z1. Okay. This is the knot. This is a Heegaard diagram of this knot, the brown knot that I drew here, and this is the trefoil knot. Okay, if you just forget about the rest of the stuff, this was the trefoil knot. And yes, that is the way, that is a Heegaard diagram of the trefoil. I don't know if someone has something. Oh, I have to go. Okay, sorry. Thank you. I thought it was a question. Okay, so yes, so we have our Heegaard diagram for a knot. And now we are going to, D is, recall the number of curves, this genus plus the k that I choose -1, d was the number of curves. And now we have this d copies, the Cartesian product of d copies of the surface, which is this, it's a manifold of dimension 2d, okay? We are taking the copies of the surface, and now we are going to consider the symmetric product, okay? So this symmetric group acts on this manifold by permuting the factors, okay? So we have this, this symmetric product, we have this, and then here we can consider those submanifolds, okay? This is of dimension d, t alpha, which is the product of the curves, okay? And t beta is going to be the Cartesian products of the beta curves, okay? So the generators of, I need to form a complex, okay? So the generators are going to be the tuples of points in the surface coming from the intersection of t alpha and t beta, okay? Meaning points so that the tuples, meaning so that each coordinates, let's say, is in one alpha curve and one beta curve, the intersection points of those curves, of those families of curves, okay? These are going to be generators. And the differentials, what we need to do is to count pseudo-holomorphic disks, okay? Define those disks are defined some way by those generators. But
Maritania, so there's like some question on chat from Charlotte. Well, maybe you can read it or Charlotte can ask.
So at this point, we always want to choose the minimal genus, number of circles, number of points. No, there is not something like, okay, if you take the minimal genus, then things will be easier. No, in fact, there are different, you can always choose a construction so that you have 1 point. You can always choose a construction so that genus is the number of regions that your diagram have. There are existence results saying you can always find a Heegaard diagram satisfying blah blah blah, but we don't know which one is the best one to do computations. So we don't want to choose a specific property diagram, okay? In fact, you will see that we won't go very, very far with this in terms of doing computations. And yes, and the reason is that, well, I think I answered the question, right? That there is no property that you want to minimize something to get easier something. And the reason, at least not in general. So the reasons is that, well, what I was saying, that differential counts pseudo-holomorphic disks, that's in some way define those disks are bounded in some way by these generators and these curves. Well, you can get some disks and you want to count these pseudo-holomorphic disks, but the problem is here because, well, this in general, we don't have an algorithm to count pseudo-holomorphic disks, and this is quite difficult. And well, you need simplicity topology here, and well, things go very crazy. So we will see a more combinatorial. This is the idea, this is the flavor, how not Floer homology was defined at first. But if one wants to do computations, people usually use this new version of not Floer homology, which is called grid homology. Okay. And let's see how it works, because the idea is the same as with Heegaard diagrams. Let's see how it is. We have a grid diagram. In this case, well, I consider the Hopf link because we have 4 times 4, which is simpler than for the trefoil, that we need 5 times 5. Okay, so here we have the Hopf link, meaning like, I mean, 2 trivial links linked. Sorry, 2 trivial nodes linked. This is a grid diagram. And we can think that this is a toric grid diagram just by thinking that, well, we are going to identify this side with this one and this one with this one, okay? And I added some numbers here because then I will use these coordinates. And I say, well, this is 4, 1, 2, 3, and this is again 4 because I'm identifying this one with this one, okay, and the same with in horizontal, okay. So this is a toric grid diagram. It's just a grid diagram where you have identified, like you want when you want a torus. And here we can see a Heegaard diagram, and the way that we see this Heegaard diagram that we can think of it is the following. The surface is clear, is the torus, because since we are identifying, we have a surface, we have a torus, right? Then the alpha curves are going to be these horizontal curves. When you identify, you have those horizontal curves, these are alpha curves, and the beta curves are going to be like the, let's say, the meridians of the, those curves, okay? You have the torus. When you identify, you have close, in this case, 1, 2, 3, 4 alpha curves, 4 beta curves. And what are the W points? W points are going to be the circles, and Z points are going to be the crosses. Okay, and this is exactly a Heegaard diagram, as we said before. You can think of it. You go, let's say this is, imagine you have identified and you have the torus, so then you go down, out, you have this. You are just going out and in and out of the torus. Each time you have an X and each time you have a circle, okay? So this is a Heegaard diagram for in this case, for the Hoff link. Yeah, but it is, you just need the grid diagram. It is the same. You have the same information. Everything is encoded in the grid diagram. Okay. So this is a very specific kind of Heegaard diagram where, well, you have genus 1, but it's not one general grid diagram with genus 1. It's the specific diagram coming from this grid diagram construction. So in this case, this one is better for us. In this case, we have 4 W points, 4 Z points, and this is the best one for doing computations. But maybe you can get one with just 1 W point and 1 Z one, and this may be better for proving some other properties. It depends on what you are interested in, okay? So now let's continue. We wanted the generators. So recall that generators were the intersection points of, were those D tuples of the intersection of these 2 families of curves, okay? So in this case, these are just n tuples of points. We have n is the size of the grid, recall, so this is n factorial, and it is, I'm going to encode them that way. When I say, for example, the generator 2, 1, 3, 4, I mean 2, look the height 2, height 1, height 3, height 4. So I will call this generator the 2, 1, 3, 4. Okay? And all these possible combinations are the generators of the complex I'm going to construct. We have, in this case, 1, 2, 3, 4, 4 factorial generators. Okay? For example, who is generator Y? 1, 3, 4, 2. It will be 1, 3, 4, 2. Okay, this is just notation that I'm using that will be useful later. So these are generators. We have n factorial generators. And now for differential, this is clear, right? That those generators are the same as we had before. This is clear because are just those D tuples coming from those intersection of these curves. And the differential, remember that we have to count pseudolomorphic disks, and this was the problem. But Manolescu, Osvat, and Sarkar proved in 2009 that counting pseudolomorphic disks in those complicated Heegaard diagrams, this is equivalent to counting empty rectangles in grid diagrams. And what are empty rectangles? Let's see, because it is not difficult. Well, we say if we have 2 generators, X and Y, in a grid diagram, we say that X and Y determine a rectangle if X and Y coincide in n-2 points, meaning in the rest of points they coincide, but in the other 2 they are that way. X is in the northeast and southwest, and Y is like here, okay? So imagine we have this grid diagram. X is the red one and the green one is Y. Here we have this, we have 1, 2, and 3 here in those 3 positions. X and Y are the same, but in 2 positions, they are different, right? Yeah. So here, remember, we are in the torus. So these 2 generators determine 4 rectangles. This one, this one, this one, and this one, right? The same generators determine 4 rectangles, right? Because we are in the torus. So R1 is a rectangle determined by X and Y. R2, now if the rectangle is this one, the northeast corner is green and the southwest corner is green. So this is a rectangle determined by YX, not XY, but YX, okay? If you do the same for the third one, you have a rectangle, the same would you have here green and red and red. So this is between Y and X. And here, in this case, you have a rectangle between, I mean, you see it from the picture, right? It's better to see the picture than listening to me explaining the picture. So these are rectangles. And well, it is important to say that rectangles, even if they are defined just by those two points where X and Y differ, if the rest of points are different, meaning that imagine that this one is here and this one is here, then the rectangles are different, right? They are different even if the shadow, even if the yellow region is the same. Do I explain myself? That the points where they coincide, if they coincide in different points, then the rectangle is different, even if the rectangle that you draw has the same shape, because you have different generators, right? So these are rectangles, and a rectangle is empty, that we put this 0 here, if and only if it contains no other points of the generator. So here the only one is R1, because here we have this, here we have this, here we have this, okay? So yeah, so this is an empty rectangle. So now we go back to our complex. In the grid homology, the complexes are going to be the free abelian group generated by those generators whose, well, we define 2 indices. One is called Alexander index, Maslov index. So the free abelian group generated by those generators whose Alexander index is S, whose Maslov index is D. We are not going to go through that, okay? Just there are 2 indexes. Depending on, do you remember this A that we used when we defined Alexander polynomial, this winding number that we have to count? So all of this is encoding those indexes. So now we consider this, we take the differential, and the differential of a generator X is just going to count the number of empty rectangles between X and Y, satisfying some properties. There are different versions. The easiest one is those rectangles that doesn't contain any points of the generators, meaning that they are empty, and also they cannot contain neither the circles of the cross or the crossings of the grid diagram. Okay, so this is the differential. With this, once you have the differential, if you take if you compose 10, then you really get 0, so it's really a differential. You can take the quotient. And Manolescu, Osvat, and Sarkar prove that this is a not invariant. It categorifies Alexander polynomial in the sense that if you take, well, here you see, right, it got the same similar way as with John's polynomial. You need to multiply by a factor, but yes, you can recover Alexander polynomial, and this is in fact not Floer homology. So you are doing the same, okay? Well, here I have an example. It is okay. I will run a little bit. We have this example of the Hopf link. In this case, we have 4 factorial equals 24 generators. Recall that a generator, when I say, for example, 2, 3, 1, 4, I mean 2, 3, 1, 4. Okay, it is clear from the picture, right? Then how I label the generators. And now for the differentials, I need to count empty rectangles. So in this case, it's very easy because I have, these are the only empty rectangles I have. I have no other empty rectangles because they cannot have circles nor crossings. So this is what I have in these examples. So for example, for the orange one, I will say that this differentials is 1, 2, meaning the red 1, 2, whatever you have goes to 2, 1, and then the same two coordinates, because these two has to be the same. Yeah? So this rectangle is giving me two differentials, 1, 2, 3, 4, going to 2, 1, 3, 4, and 1, 2, 4, 3, going to 2, 1, 4, 3. Okay? Then with the green rectangle, for example, you have 3, 4, something, somethings goes to 4, 3, something, something. Okay, when I say something, something, I mean that they coincide here and here. Okay, and well, if you do this for each of the rectangles, you have this. So if you want to put all of this in the picture with the differentials, you get something like that. Okay. So in this case, the rank of the homology, you get, well, from here you have 4 that survive, okay? And there are 12 generators that are not here because, well, they have neither differentials arriving or going out from them. So the rank of this homology is 16, okay? And this is a quick, more or less, example on how grid homology works. And well, what is the problem here? So similar with Casanova homology, for trefoil knot, that recall it is the easiest non-trivial knot. Recall that the grid number was 5. We need 120 generators. This is the reason why I changed, and here I chose the Hoff link, because I cannot draw 120 generators, okay? So, well, this definition is not, even if it is simpler and it can be, you can put it in a computer, and we know, I mean, it's algorithmic. It's not like the pseudo-holomorphic discount definition. In this case, you know the algorithm, but it's not very good when doing computations. So some new approaches to not Floer homology appeared. Well, here we have some, one based on what they call nice diagrams by Sarkar and Wang, other in terms of resolution cubes by Oswald and Szabo, one in terms of spanning trees. Well, there is also a theorem by Oswald and Szabo saying that for every knot, there exists a Heegaard diagram of the knot, so that the generators in the Heegaard diagram, meaning those intersection points, are in one-to-one correspondence with Kaufman states of the knot. These Kaufman states are something very classical that you see from the diagrams. It's like putting a marker in each region. You take into account the regions of the diagrams, the crossing, and you need to put some markers, but it's something very combinatorial and very classical. So Oswald and Szabo proved this relation, and in fact, it is not hard to construct this Heegaard diagram with this property. So Kaufman states they form a lattice, and they are related one to the other in this lattice by something that Kaufman defined as clock moves, and Ron tried to give a new approach of not Floer homology based on this theorem, taking as generator the Kaufman states, but of course the problem is defining the differentials. So he tried to prove those differential in terms of clock moves, but this was not correct. In fact, well, I found that it is not it's not invariant under Rademeister 2. So it's not a link invariant. And well, this was part of my thesis. And well, with Louis Kaufman, one project that we are trying to do is to generalize those clock moves to give a new approach of not Floer homology based on Kaufman states. But well, this project is, I think, is quite ambitious, and it's still in the first steps. But yeah, that is an idea of what we something we would like, that would be nice to have. So this was all I wanted to tell you today. So thank you.